So dining philosophers problem is the last classic synchronization problem that we'll look at this week. In this problem, assume that five philosophers are seated around a circular table in the dining philosophers problem, and each philosopher has a plate in front of them, and there is a chopstick between each pair of philosophers for a total of five chopsticks. The philosophers share a bowl of rice in the center of the table. So the problem is that each philosophers need two chopsticks, okay? Two chopsticks to eat rice to avoid conflicts over shared resources. Neither the philosophers on the right nor the one on the left can eat while the philosopher is eating with two chopsticks. This problem is a classic example in concurrent programming and operating systems, demonstrating the complexities of resource sharing and potential for the deadlock if not managed properly. So each philosopher in the dining philosophers problem goes through a never-ending cycle of thinking, obtaining the necessary chopsticks, eating, and then returning the chopsticks. This cyclical behavior reflects the inherent difficulty in managing shared resources among processes without encountering problems like deadlock or starvation. The problem is allocating resources, specifically chopsticks, among the philosophers without causing deadlock or starvation. When all philosophers try to get their chopstick at the same time, each philosopher may obtain a left chopstick but become stuck, unable to proceed because the right chopstick they require is currently held by another philosopher. Because of this dependency, philosophers are unable to complete their eating cycle and it ends in a deadlock. Avoiding both deadlock and starvation is a critical challenge in addressing the dining philosophers problem. So a solution must be designed to ensure that philosophers can access the necessary resources without interfering with another. Various synchronization mechanisms such as semaphores or mutexes are commonly used to coordinate access to shared chopsticks and prevent conflicts. Actually, the problem is an honest representation of the complexities involved in managing resources in a concurrent system. It emphasizes the careful coordination required to provide fair access to shared resources while avoiding scenarios that might block the progress of individual processes, as seen in the described deadlock situation. So the solutions to dining philosophers problem frequently involve careful planning and implementation of strategies to provide access to resource in a way that avoids both deadlock and starvation. So several solutions can be used to solve the deadlock problem in the dining philosopher scenario. The following are some proposed solutions. So we may limit the number of philosophers. So one approach is to limit the number of philosophers who can sit at the table at the same time. Okay. So allowing no more than 4 philosophers to be present at the table at any given time, for example, can prevent the deadlock scenario from occurring. By limiting the number of participants, the likelihood of all philosophers attempting to obtain their chopsticks at the same time is reduced. And secondly, both chopsticks must be available. Another solution is to change the conditions under which philosophers can pick up both chopsticks. Instead of being able to pick one chopstick at a time, a philosopher can only pick up both chopsticks at the same time. This necessitates the philosopher entering a critical section to ensure that both chopsticks are available before eating. This change reduces the likelihood of acquiring one chopsticks and becoming stuck for waiting the other chopstick. So in the last one, an asymmetric solution differentiates the behavior of odd-numbered and even-numbered philosophers. Odd-numbered philosophers pick up their left chopsticks first, followed by the right, while even-numbered philosophers pick up the right chopstick first, followed by the left. This asymmetry eliminates the possibility of cyclic dependency, which could lead to deadlock. It prevents philosophers from attempting to obtain the same chopsticks at the same time, and it reduces the likelihood of conflicts. So let's examine the first solution. The dining philosopher solution introduces a strategy to avoid deadlock by admitting only 4 philosophers at a time to attempt eating. This approach ensures that at least one philosopher can always eat, and when the other 3 of them are holding one fork each and preventing a circular dependency. This solution introduces a semaphore T. Okay. Which limits the number of philosophers sitting at the table to 4. So T count is initialized to 4, and it allows up to 4 philosophers to simultaneously engage in the eating process. Each philosopher's process follows a cyclic routine of thinking, attempting to enter the critical section to eat, and then releasing the sources. In the thinking phase, it represents the philosopher's thinking phase before attempting to eat. And after that, we see wait T operation. This acquires the semaphore T, and it limits the number of philosophers to 4 at a time. In this line, in this 2 line, okay, they take the ownership of the top 2 chopsticks necessary for the philosophers to eat. The modulo operations ensures that the index wraps around in a circular manner, and also it represents the philosopher's eating phase. At the end, after the critical section, we use these 2 lines, and they releases the acquired chopsticks after eating, making them available for other philosophers. At the end, we increase T value by calling signal T, okay? And it releases the semaphore T, allowing other philosophers to enter the eating phase. And it goes forever, which indicates that the process will continually repeat the thinking, eating, and releasing actions in an endless loop. This solution avoids deadlock by allowing only 4 philosophers to attempt eating at the same time. And the solution provides a mechanism to coordinate philosophers' activities and prevent conflicts over shared resources by using semaphores to control access.